You move one coin, then another, and suddenly the whole puzzle locks up. Three saucers, five coins, perfectly simple rules. And yet the number of moves explodes so fast that one famous version supposedly outlasts the world itself. Why? Imagine three saucers on a table and a tiny tower of five coins stacked on the first one. Each coin is a different size, with the biggest at the bottom and the smallest balanced on top. The challenge sounds innocent enough. Move that entire tower from saucer 1 all the way to saucer 3. But with a stack this tidy and this delicate, even the first move already feels like it might matter more than expected. Here is where the puzzle tightens. You can move only one coin at a time. The middle saucer is allowed, so you do get a temporary parking spot. But there is one strict restriction that changes everything. A larger coin can never sit on a smaller one. Suddenly, this is not just shuffling coins around. Every move has consequences, and a move that looks helpful now can block the entire tower a few seconds later. So now comes the real question. What is the absolute smallest number of moves needed for 5 coins? Not just any solution, but the best possible one. And once you ask that, the puzzle opens up even wider. What if there are n coins instead of 5? Is there a general rule hiding underneath? And what happens in the famous giant version with 64 rings? It starts to feel less like a game and more like a mathematical trap, doesn't it? The key insight is that the largest coin is stuck until everything above it gets out of the way. You cannot touch that bottom coin first, because 4 smaller coins are sitting on top of it. So before the biggest coin can make even one move, the top n-1 coins must be transferred to the spare saucer. That makes the puzzle feel smaller for a moment, because moving n coins secretly contains the whole problem of moving n-1 coins first. Once you see the bottleneck, the entire job splits into 3 unavoidable stages. First, move the top n-1 coins away so the largest coin is free. Second, move that largest coin exactly once to the target saucer. Third, rebuild the tower by moving the n-1 smaller coins back on top of it. Nothing extra, nothing optional. Every valid solution has to pass through these same 3 checkpoints in exactly this kind of order. Now translate those 3 stages into counting. If m of n means the minimum moves for n coins, then stage 1 costs m of n-1. Stage 2 is just one move for the largest coin. Stage 3 costs m of n-1 again. Put that together and you get m of n equals 2m of n minus 1 plus 1. And the smallest starting case is simple. With one coin, m of 1 equals 1. Let's build a few cases and watch the numbers grow. One coin takes one move, 2 coins take 3, 3 coins take 7, 4 coins take 15, 5 coins take 31. That sequence is not random at all. Each result is the previous one doubled, then increased by 1. The recurrence is now showing its personality. Instead of counting moves one by one, we can see a clean growth pattern emerging right in front of us. From here, the pattern snaps into a compact formula. The move counts line up with powers of 2, always just one less. That means the minimum number of moves for n coins is m of n equals 2 to the n minus 1. It matches every case we listed, and it also fits the recurrence perfectly, so the puzzle is no longer a maze of legal moves. It has become a simple rule you can compute directly for any stack size. Now plug in the puzzle we started with. For 5 coins, the formula gives m of 5 equals 2 to the 5 minus 1. That is 32 minus 1, which gives 31. So the smallest possible number of moves is 31, not 30, and not some messy guess you discover by trial and error. The structure of the puzzle forces that answer. Once the recurrence is clear, the 5-coin mystery resolves into a neat and exact count. Now for the legendary version. If the stack has 64 rings, the same rule gives m of 64 equals 2 to the 64 minus 1. That works out to 18 quintillion, 446 quadrillion, 744 trillion, 73 billion, 709 million, 551,615 moves. Even at one move every single second, the total time is about 585 billion years. That is wildly longer than human history, longer than civilization, even longer than the age of Earth. A tiny puzzle on 3 saucers turns out to hide truly cosmic growth. This puzzle hides a brutal truth. Simple rules can create impossible-looking growth. If that kind of logic twist hooked you, click the video on screen for another puzzle built on hidden assumptions and mind-bending inevitability.